The Lagrangian equation of the Standard Model. This equation is our closest description of a theory of everything. And when I say everything, I mean everything. But how? Let me back it up. To understand the Standard Model, you need to know two things. First, what the fundamental particles are. Everything's made of atoms, and atoms are a lot like this Russian nesting doll. You crack it open, and you see there's more to it. Because inside the atom, there's a nucleus and an electron orbiting it. Inside that nucleus, there are protons and neutrons. Crack open the protons and neutrons, and you get quarks, which come in 6 different types or flavors. There's up and down, charm and strange, and top and bottom. They're the elementary particles of the nucleus, but orbiting the nucleus, there's another particle, the electron. It's part of a class called leptons, and there's 5 more. The electron neutrino, the muon neutrino, the tau, and the tau neutrino. All these 12 particles that I've described so far are called the fermions. But there are 5 fundamental particles left, the bosons. The first 4 bosons are the gauge bosons. They're the carriers of the 4 fundamental forces, the other part you need to know. They are the strong, electromagnetic, weak, and gravitational force. The gluon carries the strong force, which glues quarks together. The photon carries the electromagnetic force, responsible for the attraction and repulsion of the electric charge. The W and Z bosons work together to carry the weak force, which makes things like beta decay and nuclear fission happen. We're talking atom bombs here, people. But wait, there's one last fundamental force, gravity. I mean, we know it exists, but we're out of gauge bosons. So, does the Standard Model have a flaw, or have we just not discovered the graviton boson yet? Moving on, the last boson, the Higgs boson, is the only scalar boson. And it's often called the God particle because it has the property of giving all matter its mass. So now that we have all that covered, let's take a look at this equation. Oh boy. To actually solve that, you probably need a couple of PhDs. But the concept's actually pretty simple. In physics, we want to know the status, or the position and velocity, of a system, which is basically anything comprised of smaller parts. We want to know the status of a system, particularly the system being an atom, because that allows us to predict where it's been, where it is right now, and where it's going. It allows us to predict the behavior of the atom. But how do we find them? Well, lucky for us, it's easy if you know a system's energy. But systems are made of so many parts that you can't measure the energy collectively. But the best way to handle big problems, split them into smaller parts. Like an atom, take that for example. It's made of 17 parts, but if we can find the energy of each part individually, we can add it up to find the energy of the entire system. And if you know the energy of the entire system, you know the position and the velocity. And if you know that, you have the status. Being able to predict what an atom, the building block of everything, is going to do gives us the opportunity for so much knowledge. And that is why the Lagrangian form of the Standard Model tells us about everything. Well, almost.